Osmosis. I think most people have heard of osmosis. If you ever watch television or even listen to the radio, there's a lot of people pushing reverse osmosis water purifiers, right? You hear that a lot. Osmosis is a very important concept. It's the flow of solvent from a less concentrated solution to a more concentrated solution. And this occurs when you've got solutions with a high concentration. They're going to pull water. I know about osmosis, but when my husband and I first got married, he was working late because he was still working on his PhD, and I made one of our cheap favorites, which is teriyaki hot dogs. Okay, so you make your own teriyaki sauce. I'll give you the recipe if you want. It's really easy. And you score the hot dogs. You can be as fancy as you want, but you just cut their skins a little bit, and you boil the hot dogs in teriyaki sauce, and it makes them taste all fancy, and yet they're really cheap, right? And you eat it on rice. So I made teriyaki hot dogs for dinner, and I ate my dinner, and he was late as usual, and so I just left the teriyaki hot dogs in the sauce, not really thinking what was going to happen. And by the time he came home, they were hard as rocks because of osmosis. Teriyaki sauce contains a lot of soy sauce. It's got a high salt content. There's also a high sugar content in teriyaki sauce. So high concentration of solutes compared to the concentrations of solutes in the hot dog. And so it pulls the water out of the hot dog and effectively dehydrates the hot dog. So, yeah, those went in the trash. There's a lot of sodium in hot dogs, but there's more in soy sauce. And then you've got the sugar in there too. So it's a double whammy. And so, like, you know, when you're marinating meat and stuff, we like to make teriyaki chicken. You don't want to soak it too long. Sometimes longer is not better. If you've ever smoked salmon, you know that usually you soak it in a brine solution first, and that's to pull some of the water out of it so it's not so juicy, because you don't want your smoked salmon to be juicing all over the place. Anyway.
But what about brining turkey?
Brining turkey would do the same thing. It'll draw some of the liquid out. Now the turkey flesh is really thick, so it's not going, it's not going to pull out all the juices of your turkey. I know it's juicy on the inside. So then, there's more complicated factors. There's more complicated factors in brining turkey. We could investigate those, but we're not going to do that right now. You probably also know that if you were stranded in a boat on the ocean, you should not drink ocean water, right? Not because it's got stuff and pollutants in it, but because it will kill you, right? Not immediately, but slowly and painfully. Seawater has a lot of salt in it, and drinking salt water actually makes you more thirsty, makes you more dehydrated than if you didn't drink any water. And this is why. So here is your intestine, picture of your intestine. And here is the inside of your intestine, and here's the inside of your body. Okay? So when you have water in here, nope, I've got it backwards. This is you drinking salt water. Yeah, this is you drinking the salt water. Here's the salt particles in here. And this is inside your body. And the salt water has a higher concentration. They say it's a thirsty solution. It's going to pull water. Your intestine is a semipermeable membrane, which means that it will allow water to pass back and forth and other small molecules. And over here in your blood and whatever else is on the other side of your, I'm not a biologist, of your intestinal wall, there's a little bit of salt, but there's a lot of water. And the concentration here of salt is really important. And so you get a lot of salt water in your intestines, and it's going to pull water out of your tissues. And that will cause you to become more dehydrated. So drinking salt water, your body doesn't get water, your body loses water because of osmosis. Here's a more scientific look. We can make this a tube. These were called U-tubes because they're shaped like a U, and now that has a completely different meaning, doesn't it? So here we have a tube that's shaped like a U. And in the middle here is a semipermeable membrane. And on the one side, we've got pure water, and on the other side, we have salt water. And initially, the levels of water are the same. Now, if we didn't know what was in here and we didn't know about osmosis, what would we expect the levels of these liquids to do? Stay the same, right? We've looked at things with pressure and how the levels changed, but both sides of this tube are open to the atmosphere. Pressure is not an issue here. But if we let this go, after a while, we see that the level on one side goes up and the level on the other side goes down. We didn't do anything to it. It happened by itself. The reason is osmosis. This side is saltier. It's more concentrated. And so the water will flow from the less concentrated to the more concentrated side, causing the level of this liquid to go up. Now, it's only going to go up a certain amount because pressure and gravity says that it should be equal, right? So it will not go up until all of this water is gone. It will go up a certain amount. And the amount that it goes up, the difference in the height here, is reflective of something we call the osmotic pressure. The greater the difference in concentration between these two solutions, the higher the liquid in this arm will rise. And so this osmotic pressure is a measure of the difference between the concentrations in the two solutions. Any questions? Osmotic pressure is a colligative property. Colligative properties depend on the concentration, the number of solute particles, not on what they are. Okay? So the more concentrated the solution, the greater its osmotic pressure. The membranes of cells are semipermeable, which is how they can, get things in and out, even though they don't have like doors and stuff, right? If you put a living cell in seawater, it's going to lose water through osmosis and become dehydrated. But if you take an organism that's accustomed to living in seawater and put it in fresh water, it's going to absorb a lot of water and bloat up, and that'll probably kill it too. Blood cells are sensitive to concentrations of solutes. And so for those of you who are more, health-related fields, you maybe know some of this. So this is what normal blood cells look like. They're kind of donut-shaped. I've got this indentation here, which probably has a name. So normal red blood cell, your blood has a specific concentration of solutes in it. You need sodium. You've got sodium and chloride and dissolved things in your blood, right? And so what we call an isotonic, iso is a prefix that means the same. An isotonic solution is one in which the concentration of solutes in the surrounding fluid is the same, equal to that within the cell. So in an isotonic solution, red blood cells are happy. They remain the same shape, the correct shape that they're supposed to be. If we put them in a hypotonic solution, where the concentration surrounding them is lower, what happens? They swell up. So if we put the red blood cells in pure water, water is going to flow into the cells. The way I think of it is, nature doesn't like things to be different. It's trying to level things out. There's more complicated reasons, but this makes sense on a very easy to understand level. There's a concentration, high concentration here and a low concentration there, and it's like, hey, wait a minute, can we make this equal? And it can, at least partially, because the water can go through the semipermeable membrane. So the cells absorb water, and if this keeps going on, what's going to happen? They will burst and die, and that's not good. So hypo is a prefix meaning less. So the solution around it has a lower concentration. Hyper means more. Hyperactive is more active, right? Hypertonic, surrounding fluid is more concentrated. And so then you get this funky looking thing. So the water is flowing out of the red blood cells, and they're shrinking and shriveling, and that's not good either. That's why when you go to if you're in the hospital and they're giving you an IV, I think it's 0.9% sodium chloride. And then they put whatever else they need in there, because whatever else they put in there is going to be relatively low compared to the salt. But they want to put an isotonic solution into your blood so that they're not causing your red blood cells to shrink or explode. I wouldn't like exploding blood cells. It'd be bad. End of chapter, finally. Chapter in review.